Hello, my name is Anna de Graaff. I am a PhD student at Leiden Observatory, and here I work on the evolution of massive galaxies through the viewpoint of galaxy scaling relations. And today I'll be talking about some results from two recent papers I put on archive from the LEGA-C Survey. Now, there are, of course, many different ways of looking at galaxy evolution through a statistical point of view. And stellar mass functions, for instance, tell us that galaxies grow in mass with cosmic time, and that this growth depends on the mass itself and on the colors of galaxies. Similarly, from the mass-size relation, we know that galaxies grow in size and that this growth is much more rapid for quiescent galaxies than for star-forming galaxies. Now, what I set out to do is to understand a little more about how the structural properties of galaxies evolve with cosmic time. And we can do so by adding in a third parameter, and that is the galaxy kinematics. You then obtain the fundamental plane. So this is a scaling relation between galaxy size, surface brightness, and kinematics. And here you see quite an old plot showing how local early type galaxies lie in this parameter space, and you see they clearly trace a very tight plane. Now, the fundamental plane has some interesting properties that are related to the structural and stellar population properties of galaxies. One of these is best traced by the redshift evolution of the plane. So here you see an edge-on view of the fundamental plane. So you see this tight sequence. And you see as this evolves with redshift that the sequence also evolves. So the 0 point of the plane changes. Now, this 0 point is directly proportional to the mass-to-light ratio of galaxies. So what we're seeing is that the mass-to-light ratio of galaxies decreases towards high redshift. Now, what you also see is that the data points toward high redshift become very sparse. And this is because measuring stellar kinematics at high redshift is extremely difficult. And so far, studies of the fundamental plane have therefore really focused on galaxies that are either very bright or lie in very high density environments. So what we'd like to understand is how this evolution looks like for a more representative sample of galaxies. And this is where the LEGA-C survey really comes in. So LEGA-C is a deep spectroscopic survey of massive galaxies in the cosmos field. It targets about 3,000 galaxies at a redshift of about 0.8. So it's a look-back time of about 7 gigayears. And it is K-band selected. So this means we get a sample that spans a wide range in colors, structures, morphologies, and so on. And on the right, you just see some example spectra from the LEGA-C survey. So you see all these nice high signal to noise absorption features, from which, among many other things, we can measure very robust stellar kinematics. Of course, being in the cosmos field, there's also a great wealth of ancillary data available. So we have galaxy morphologies available, but also multi-wavelength photometry, from which we've performed SED modeling to obtain stellar masses, star formation rates, and so on. So what do we do with these data then? Well, we can just first of all take a look at the fundamental plane at a redshift of 0.8, and that's what you see here. So on the left, you see what the quiescent sample looks like, selected by UVJ columns. And you see they form this very tight sequence, just like they do at redshift 0. So this is kind of expected. Now, what is interesting is if we also include star-forming galaxies, you see that they also trace a similar sequence, but with a slightly different 0 point and much larger scatter. So this already tells us something about differences in stellar population properties and structures between these two populations. So how does this compare to redshift 0 then? Well, in the following way. So we find a very strong evolution. So here you see the evolution of the 0 point of the plane, which is proportional to the mass-to-light ratio. So what this shows is that galaxies at higher redshift have lower mass-to-light ratios. Now, of course, this is not unexpected. Galaxies at high redshift are younger and therefore brighter at short wavelengths. This is tracing the G-band. But the question really is to what extent this change in the mass-to-light ratio is due to stellar population evolution or evolution in the structural properties. Now, to evaluate this, we can first of all go back to the previous plot. So this is showing relation between size, dispersion, and surface brightness. But if we replace the surface brightness by a stellar mass surface density, then we obtain the so-called mass fundamental plane. And this is interesting because when you look at a mass fundamental plane, you find that all galaxies lie on the same plane. So this is irrespective of their color, structure, dust properties, and so on. And when I say the same plane, I don't just mean the same 0 point, but they also have the same scatter about the plane. And so they really form a unimodal distribution in this parameter space. This is more clearly shown in this plot. So here we look at the fundamental plane, different wavelengths. So first of all, the G band that I showed before, and you see that the scatter is quite high, especially so for star-forming galaxies. Which is of course expected. Star-forming galaxies have a wide range of dust attenuation, star formation activity that really changes the luminosity at short wavelengths. As we go to longer wavelengths, you see that this effect becomes smaller from stellar populations. And then when we take into account stellar populations properly and obtain a mass fundamental plane, you see that the scatter really decreases and that star-forming and quiescent galaxies have approximately equal scatter about the plane. So we can then ask the final question, and that is, how does this then evolve towards low redshift? And that is in the following way, that it really doesn't. And this is quite striking. So this is just showing the evolution of the 0 point of the mass fundamental plane, which now, rather than tracing the evolution in the mass to light ratio, traces the evolution in the dynamical mass to stellar mass ratio. And you see that this is basically flat, both for star-forming galaxies and quiescent galaxies. So what this means in practice is that a galaxy of a fixed size and a fixed velocity dispersion at a redshift of 1 is the same as a galaxy at a redshift of 0. Now, of course, this does not mean that a galaxy cannot evolve. It does, but for a fixed size and velocity dispersion, they are the same. But beyond this, this also has bigger implications. So we find that massive galaxies lie on the same scaling relation across at least 7 gigayears of cosmic time. And this means that progenitors and descendants lie on the same scaling relation. So galaxies are very highly confined in a narrow range in parameter space. So for instance, when a galaxy quenches or merges with another galaxy, it is constrained to do so in a very specific way to move along the fundamental plane. So this puts pretty tight constraints on our models of galaxy evolution, and therefore provides a very good tool to test theories of galaxy evolution. Now, lastly, we can actually also use the fact that the fundamental plane does not evolve to use the fundamental plane as a tool to track galaxies across cosmic time in a statistical sense, so that we can actually measure the evolution in, say, the size or the mass with minimal impact from progenitor bias. If you have any questions, then please contact me on the Slack, and thanks for watching.